In this video, we are going to be taking a look at a special case of a discrete random variable and a discrete probability distribution. Right, what we're going to be looking at in this video is what is called the binomial distribution. Before we kind of get into the math and everything, we do need to talk about how we get a binomial random variable. Right, so our probability distribution, the binomial probability distribution, is going to come from a binomial random variable. Binomial random variables come from binomial experiments. So the first thing that we're going to do is talk about some of the conditions for a binomial experiment. Right, so if a process or an experiment matches these conditions, right, then we can use the binomial probability distribution to find those probabilities. All right, but without further ado, so these are the conditions for a binomial experiment. All right, the first one is that there are only two outcomes for each trial of the experiment. All right, so this is where the bi in binomial comes from. We have two outcomes for each trial. Those outcomes, they can be whatever they are, but we are going to be referring to them as success and failure. Right, so those are going to be kind of our two outcomes. As long as we can create a way for us to have a success and have a failure, right, then we can have two outcomes. Right, so to explain a little bit more what I mean by that, let's say that our trial for this binomial experiment is that we are going to be flipping a coin, right, and seeing which side it lands on, right? Well, that has two outcomes, right? Heads or tails, right? So that's good, right? We're already off to a good start because we've only got two outcomes for each trial. But we would define one as a success and one as a failure, right? We might say heads is a success, tails is a failure, right? We might do it the opposite way, just kind of depends on what we are trying to look at. Right, but we don't have to limit ourselves just to things that naturally give us only two options. Right, so to still keep it simple, but to make it a little bit more complicated than with just flipping a coin. Let's say we were rolling a die, right? Just a six-sided die, right? Well, that doesn't naturally have only two outcomes, right? It has six outcomes. But we could define a success and a failure in such a way that we only have two outcomes, right? We could define a success as rolling an odd number and a failure as rolling an even, right? That way we have only two outcomes for each trial, right? We could say a success is rolling a 1 and a failure is rolling 2 through 6, right? We can establish that so that we only have two outcomes. All right, but that is an important condition. All right, if there are more than two outcomes for each trial, then it's not a binomial experiment. All right, so we have to have only two outcomes. All right, the second condition is that the experiment consists of n identical trials. Right, so we're not just flipping a coin once, all right, we're flipping it multiple times. We're not just rolling the die once, we're doing it multiple times. Right? usually, I mean, you could theoretically use this if you're only doing one coin flip, only one die roll, but it's more complicated than it needs to be if that's all you're looking at, right? But we can have, all right, so, you know, say we're going to flip the coin 6 times, right? Or however we are going to do that. All right, but we are going to have in identical trials, and they do need to be identical, right? We're flipping a coin 6 times in a row. We're not flipping a coin, rolling a die, drawing a card, right? That's not going to be a binomial experiment, right? They have to be identical. Let's see. I think I can fit this next one in here. All right, so 3, the probability, actually, that's already getting pretty crowded, so we're just gonna erase this and then go to the next thing. All right, so those are the first 2. Let's now look at the third one. All right, so our third condition is that the probability of a success is denoted P, all right? That's a lowercase. Oh, I left out a key piece of verbiage. All right, so the probability of a success on any one trial, all right? So this is the probability of a success on a single trial, all right, is denoted by a lowercase p, and it does not change from trial to trial. All right, so that's our third one, and I'm going to go ahead and put up the fourth one as well because they are fairly similar. The fourth condition is that the trials are independent of one another. All right, so really they're saying very similar things. Our third condition is saying that we've got a set probability for success, right? These trials are identical, so their probability, the probability of a success has to be the same for all of them. The probability of a failure has to be the same for all of them, right? And they cannot change, right? That probability does not change from trial to trial, right? Then for number 4, we're saying the trials are independent of one another, right? So if we remember back from chapter 5, what does it mean if two things are independent? It means that they don't affect each other, right? So a success or failure on one trial is not going to affect the probability of a success or a failure on any other trial. Right, so again, just saying, right, that probability is not changing, right? And really by the fact that the probability of a success cannot change from trial to trial, by definition that means they are independent of one another, right? Because it doesn't change. All right, and then the fifth and final condition, really more of just kind of describing what our random variable is, right? But the binomial random variable is the count of the number of successes in trials. All right, so how many of the trials that made up our experiment, right, how many of those did we have a success? All right, that's what we are asking. right? So if, just to give a very brief little example, let's say that we were going to flip a coin 3 times, right, and see how many times we got heads, all right? And we wanted to find some probabilities about that, right? So let's say we would define a success as a heads. So we would flip the coin 3 times, and our random variable is just how many heads we got, right? So it could be anywhere from 0 to 3, and that would be our random variable. So just however many of those we got. All right, but that is our 5th condition. All right, so now let's actually look at how we're going to be calculating these probabilities, because that's what we're here to do. We're looking to calculate probabilities, right? But it is important to know these conditions for our binomial experiments. We are going to have a separate video of an actual worked out example. And so in this one, we're just going to put up the conditions, and then I'm going to put up the formula for finding probabilities for a binomial random variable. And then we're also going to talk a little bit about expected value and variance. But again, we won't have any actual math happening in this video. All right, but without further ado, let's go ahead and say, all right, we are looking at the binomial probability distribution function. All right, so I went ahead and abbreviated that, but well, I didn't abbreviate binomial. Binomial probability distribution, and then I didn't abbreviate function either, right? But it's the binomial probability distribution function. This is how we're going to know how to calculate a probability for a binomial random variable. All right, so just starting off with our standard probability statement, right, the generic one. Then we're going to go on. Actually, I'm just going to write it out, and then we'll talk about it. All right. So I go ahead and promise you that this is not as bad as it might look. So let's just kind of go through here and look and identify some important features. Right. So one, right, the first one we might be interested in is n, partially because it's the first thing up. Right. So what is n? Right. Well, if we go back to those conditions, we know n is the number of trials. Right. Our experiment as a whole is made up of n identical trials. So this n is just the number of trials. Right. So if we're flipping a coin 3 times, right, n would be 3 because we're doing our trial flipping the coin 3 times. Right. So n is the number of trials. Right. X. Right, all of these x's are the same thing, right, as well as this one, right? This is kind of what we're actually looking at. So whatever the probability is we're looking at, if we're looking at what is the probability that we get 1, right, heads out of these 3 coin flips, then that would be probability x equals 1, right, and we would put a 1 in each of these spots where we have an x. So x is the number of successes. Right, and this whole function here, this is just our combinations function, so NCX. We talked about that at the end of the last chapter, at the end of chapter 5, right? So this is just a function we're going to find in our calculator. If you've got a Texas Instruments, it's going to be under a probability menu. If you've got a kind of more basics or scientific calculator, it's probably up near your second button. And if you have a kind of graphing calculator, it's going to be in some menu somewhere. And if you have a Casio, it's a secondary function. Usually I think it's around where the numbers are. It might not be a secondary function of one of the numbers, but it's around that area if memory serves. Right? It also might not look like NCX on your calculator. I think for Texas Instruments, it's NCR. I think that's probably something similar for Casio as well. All right, but again, that's just going to be a function that we're just going to be plugging into our calculator. All right, then P, this is the probability of success. All right, so we also learned that in those conditions. All right, so that only leaves us with a couple of things. All right, so one, and I'm not going to write these next two things down because we can just kind of figure them out from context. All right, but if you would like to write them down, please do. All right, I guess I couldn't really stop you from writing them down anyways. I don't know why I felt like I needed to give you permission. But, all right, so 1 minus P, if P is the probability of success, right, 1 minus P, that's the probability of the complement of a success, right? Or a simpler way of saying it is a failure, right? What's the probability of a failure? Well, it's the probability of not succeeding, and that's what 1 minus P is telling us, right? So 1 minus P, that's the probability of failure. When we get into actual calculation for this, I suggest that you go ahead and find this kind of separately and don't write it in as 1 minus then whatever P is. It just makes it bulkier than it needs to be. So I would suggest just doing 1 minus whatever P is and then grabbing that and then writing that down so you can just grab it later. All right, and then we have N minus X. All right, so nothing terribly new. It's just a couple of things. All right, what this is, right? So N we know is the number of trials, right? And we're subtracting from the number of trials X, which is the number of successes, right? So if we subtract the successes from the number of trials, then we're left with all the trials where we didn't succeed, right? So this N minus X is the number of failures. Right, so we're taking the combination, right? So the combination is essentially saying how many ways can we have this number of successes out of this number of trials, right? So how many ways can this happen, right? Can we take 1 or 2 or whatever that X is? How many ways can this happen, right, when we're drawing them from N trials? Right, we're multiplying it by the probability of a success raised to the number of successes times the probability of a failure raised to the number of failures. All right, that is what our binomial probability distribution function is. All right, so again, we're going to take a look at that as example-wise in another video. But for now, let's talk a little bit about expected value and variance. All right, so the expected value for a binomial random variable, really the expected value and the variance are going to be very easy, all right? So we have a slightly more difficult process for finding a probability for the binomial distribution, although once you start using it, it's really not that bad, right? But the calculations for expected value and variance are much easier than what we were doing beforehand for just generic discrete random variables. All right, so for the binomial a binomial random variable, right, the expected value of our variable is simply the number of trials times the probability of success. All right, that's all it is. All right, then the variance for a binomial random variable is almost just as simple, right? And that variance calculation is the number of trials times the probability of success times the probability of failure. So N times P times 1 minus P. Right? We can use these to find the expected value and variance of a binomial random variable, but that's it. All right? So we cannot use these, all right, for other discrete random variables. One, we're probably going to understand because we're not going to have a number of trials. We're not going to have a probability of success, right? But This only works for the binomial random variables, right? It doesn't work for anything else, right? However, you could do, if you wanted to, use the other methods that we've talked about, the kind of longer formulas that we did in previously in this chapter, right? You could use that to find the expected value and variance for a binomial random variable, but it's going to be faster, it's going to be simpler to use these formulas. Right, and we can interpret these just like we've done with everything else, right? So the expected value, this is telling us the same thing that the expected values we calculated earlier were telling us, right? The variance, same thing, it's telling us the exact same thing. We're going to interpret it the exact same way. And of course, if we take the square root of this, we can find our standard deviation as well if we so desire. But that is it. So that is the basics of our Poisson, or not our Poisson. That's the next thing we're going to look at. This is the basics of our binomial probability distribution. In the next video, we are going to actually work through an example of this. All right, so we can actually see it in action a little bit more, or not a little bit more, just at all. All right, so we'll actually kind of work through an example. All right, but that will be in the next video, and I will see you then.